The story of the Messerschmitt Me 262 begins not with a triumphant first flight, but with a quiet conversation in a Berlin cafe during the autumn of 1938, when aircraft designer Willy Messerschmitt met with engine pioneer Hans von Ohain to discuss an idea that seemed almost science fiction at the time: propulsion without propellers. The concept of jet thrust was not entirely new. British engineer Frank Whittle had filed patents for a turbojet engine in 1930, and Italian inventor Secondo Campini had demonstrated a rudimentary motorjet in 1940, but practical implementation remained elusive. What made the German approach different was von Ohain's breakthrough in compressor design combined with Messerschmitt's willingness to risk his company's reputation on an unproven technology. The meeting in that Berlin cafe was not authorized by the Reich Air Ministry, which considered jet propulsion a distraction from proven piston engine development. Messerschmitt was operating on his own initiative, using company funds rather than government contracts, a decision that would later save the project when official channels proved obstructive. Von Ohain, just 25 years old and recently graduated from the University of Göttingen with a doctorate in physics, carried with him detailed calculations showing that a properly designed axial flow compressor could achieve the pressure ratios necessary for sustained jet thrust at aircraft speeds. His prototype P-51 engine had already produced 1,100 pounds of thrust on a test stand, a modest figure by later standards but sufficient to convince Messerschmitt that jet propulsion was no longer theoretical. What neither man fully appreciated in that cafe conversation was how their technical ambition would become entangled with the moral catastrophe unfolding around them. Germany in 1938 was already implementing the Nuremberg laws, had annexed Austria in the Anschluss, and was preparing for the invasion of Czechoslovakia. The engineering challenge they discussed existed within a political reality they could not escape. Messerschmitt's company would soon depend on contracts from a regime committing systematic atrocities, and von Ohain's research would eventually rely on resources extracted through forced labor. Yet in that moment, they saw only the physics problem before them: how to harness the Brayton cycle in a package light enough to lift an aircraft yet robust enough to operate reliably outside laboratory conditions. Messerschmitt returned to his Augsburg design bureau with von Ohain's calculations and immediately assigned a small team of 6 engineers to explore airframe configurations suitable for jet propulsion. They worked in a converted storage room away from main design offices, their project known internally as P-1065, a deliberately obscure designation to avoid attracting unwanted attention from ministry bureaucrats who might cancel work deemed insufficiently practical. The team faced fundamental aerodynamic challenges that piston engine designers never encountered. Jet engines produced maximum thrust at high speeds where propeller efficiency declined, suggesting optimal performance in a speed regime above 400 miles per hour, territory where compressibility effects and control surface effectiveness became problematic. Early wind tunnel tests revealed dangerous pitch-up tendencies as airflow over the wing approached Mach 0.7. requiring radical redesign of the tail configuration. More critically, jet engines consumed fuel at rates 2 to 3 times higher than comparable piston engines, demanding airframes with significantly larger internal volume for fuel tanks, a requirement that conflicted with the streamlined shapes needed for high-speed flight. The design team iterated through 17 different wing configurations before settling on the distinctive swept-wing layout with 18.5 degrees of sweepback, not for transonic performance as sometimes claimed in popular histories, but to position the wing's center of pressure correctly relative to the aircraft's center of gravity given the heavy engine placement in the wing roots. This solution emerged not from theoretical breakthrough, but from painstaking wind tunnel testing at the Aerodynamische Versuchsanstalt in Göttingen, where engineers ran hundreds of scale models through smoke visualization tests to understand airflow patterns invisible to the naked eye. Meanwhile, von Ohain's engine development faced its own cascade of failures. The P-51's turbine blades, machined from conventional steel alloys, warped and fractured under thermal stresses exceeding 600 degrees Celsius, a problem that would plague jet engine development worldwide for years. Von Ohain's solution was characteristically ingenious. He collaborated with materials scientists at the Kaiser Wilhelm Institute to develop a nickel-chromium alloy with improved high-temperature strength, but production quantities remained limited due to wartime shortages of nickel. The first complete P-51 engine installed in an Heinkel He-178 airframe achieved history's first jet-powered flight on August 27, 1939, just days before Germany invaded Poland. But the engine failed after 8 minutes of operation when turbine blades disintegrated, nearly killing test pilot Erich Warsitz. This pattern of promising demonstrations followed by catastrophic failures would characterize German jet development for years. Messerschmitt, observing these struggles from Augsburg, made a critical decision that would shape the Me-262's fate. Rather than waiting for a perfected engine, he would design an airframe flexible enough to accommodate multiple engine types as they became available. This pragmatic approach meant the P-1065 design included mounting points compatible with von O'Haines's engines, BMW's parallel jet development program, and even the Junkers Jumo 004 that would eventually power production aircraft. The airframe itself represented conservative engineering in revolutionary packaging. Messerschmitt deliberately avoided radical innovations that might introduce additional failure points. The wing employed conventional stress skin construction with aluminum spars and ribs. The fuselage used semi-monocoque design proven on earlier Messerschmitt fighters. Even the landing gear retracted in a conventional manner rather than employing novel mechanisms. Only the power plant placement, in the wing roots rather than the nose, represented genuine innovation, and even this choice emerged from practical necessity rather than theoretical elegance. The jet engine's diameter made nose mounting impossible without creating an aerodynamically disastrous frontal area. By late 1940, the P-1065 design had matured sufficiently for Messerschmitt to present it to the Reich Air Ministry, but the reception was cool. Ministry officials, focused on immediate needs for the Battle of Britain, saw jet fighters as irrelevant to current combat requirements. More significantly, Hermann Göring, head of the Luftwaffe, had developed a personal skepticism toward jet propulsion after witnessing early engine failures. He reportedly told Messerschmitt during a 1940 meeting, "I have seen enough rockets and jets to last a lifetime. Give me reliable aircraft that can be built in numbers, not laboratory curiosities." This attitude reflected a broader strategic misconception within German leadership: the belief that quality could compensate for quantity in industrial warfare, a fallacy that would prove catastrophic as Allied production capacity dwarfed Germany's. Messerschmitt persisted despite official disinterest, continuing development with company funds and a small team working under the guise of high-speed research. The breakthrough came unexpectedly in April 1941, when Luftwaffe test pilot Fritz Wendel made an emergency landing of a Messerschmitt Bf 109 near the Augsburg factory after combat damage over France. During debriefing, Wendel mentioned to Messerschmitt that German pilots were increasingly outclassed by new British Spitfire MKV variants in speed and climb performance, a vulnerability that threatened air superiority over Western Europe. Messerschmitt seized this opportunity, arranging a private demonstration flight of the P-1065 prototype, now designated Me-262V1, for Wendel the following week. On April 18, 1941, Wendel taxied the prototype, powered by a single Junkers Jumo 210 piston engine in the nose since jet engines weren't yet ready, to the end of Augsburg's runway, applied full power, and was astonished when the aircraft lifted off after a takeoff roll half the length required by the Bf 109. Though flying on piston power alone, the Me-262's aerodynamic cleanliness was immediately apparent. Wendel's enthusiastic report to Luftwaffe headquarters, describing the aircraft as the future of fighter aviation, finally attracted serious attention from ministry officials who had previously dismissed the project. Within weeks, development funding was approved and priority status granted, though with the caveat that jet engine development must demonstrate reliability before full production approval. This conditional support created a development bottleneck that would haunt the program for years. Airframe development raced ahead of engine maturity, creating aircraft that were ready to fly but lacked reliable power plants. The first true jet-powered flight of the Me-262V1 occurred on July 18, 1942, with test pilot Fritz Wendel at the controls and two BMW P.3302 jet engines, predecessors to the production BMW 003 mounted under the wings. The flight lasted 6 minutes before Wendel shut down both engines and glided to a landing after experiencing violent compressor stalls at full throttle. Post-flight inspection revealed turbine blade failures in both engines, but Wendel's report emphasized the aircraft's handling qualities. Despite engine troubles, the airframe demonstrated exceptional stability and control response at speeds exceeding 450 miles per hour, speeds where conventional fighters become dangerously unstable. This assessment proved prophetic. The Me-262's greatest strength was not raw speed, but the combination of high speed with docile handling characteristics, a quality that would make it deadly in combat despite its limitations. Yet the engine problems persisted. BMW's 003 engine suffered from turbine blade failures, combustion chamber cracks, and compressor stalls that made it unreliable for operational use. Messerschmitt's team reluctantly shifted focus to the competing Junker's Jumo 004 engine, which showed marginally better reliability despite its own problems with turbine blade life and throttle response. The Jumo 004's development was itself a story of engineering compromise under resource constraints. Designer Anselm Franz faced severe shortages of high-temperature alloys due to nickel and chromium being prioritized for U-boat diesel engines and tank armor. His solution, using mild steel for turbine blades with aluminum paint to reflect heat, was a desperate improvisation that limited engine life to approximately 25 operating hours before requiring complete overhaul. This constraint would later force Me-262 pilots to treat their aircraft not as frontline fighters but as precious assets to be preserved, fundamentally undermining their tactical utility. By late 1942, the Me-262 program had reached a critical juncture. The airframe was proven, engine reliability was improving slowly, production tooling was being prepared at Messerschmitt's Regensburg factory. Yet deployment decisions remained paralyzed by competing priorities within the Nazi hierarchy. Adolf Hitler, briefed on the project in November 1942 after viewing film footage of test flights, expressed initial enthusiasm but quickly fixated on a misconception that would prove catastrophic. He believed the Me-262 speed advantage made it ideally suited for high-speed bombing missions against Allied invasion forces expected to land in France. This idea ignored fundamental aerodynamic realities. The Me-262's wing loading and landing speed made it vulnerable during bomb release maneuvers, and its limited range restricted operational flexibility, but Hitler's intuition overrode engineering assessments. When Messerschmitt attempted to explain these limitations during a January 1943 meeting at the Wolf's Lair, Hitler reportedly interrupted, "I decide how weapons are used, not engineers. This aircraft will carry bombs." The order was given. All Me-262 production would be configured as fighter bombers with underwing bomb racks and modified flight control systems to accommodate the asymmetric loads of single bomb releases. This decision delayed operational deployment by nearly 18 months while engineers redesigned the airframe for a role it was never intended to fulfill. A delay that proved decisive as Allied air superiority became overwhelming by mid-1944. The human dimension of this period reveals the moral complexities faced by German engineers working under dictatorship. Willy Messerschmitt himself was not a Nazi Party member and privately expressed frustration with political interference in technical decisions. Yet he accepted contracts from the regime and benefited from its patronage. His chief aerodynamicist, Dr. Waldemar Voigt, maintained a careful distance from party politics while focusing exclusively on technical problems, a compartmentalization that allowed him to preserve his engineering integrity but also absolved him of broader moral responsibility. More troubling was the growing reliance on forced labor as Allied bombing disrupted German industry. By 1944, an estimated 30% of Messerschmitt's workforce consisted of concentration camp prisoners, Soviet POWs, and civilian deportees from occupied territories, people working under starvation conditions with mortality rates exceeding 20% in some camps. Company records show Messerschmitt executives were aware of these conditions yet continued to request additional forced labor allocations to meet production quotas. This reality cannot be separated from the Me-262's history. The aircraft that represented engineering brilliance was also a product of human suffering on an industrial scale, a paradox that challenges simplistic narratives of technological progress. When the first operational Me-262s finally reached Luftwaffe Test Unit Erprobungskommando 262 in April 1944, pilots immediately recognized the aircraft's revolutionary potential despite its limitations. Hauptmann Werner Thierfelder, the unit's commander, wrote in his operational report, "The Me-262 changes the fundamental geometry of air combat. At speeds above 450 miles per hour, conventional defensive maneuvers become impossible for piston engine opponents. The aircraft can dictate engagement terms, attacking when advantageous, disengaging at will." Yet Thierfelder also documented critical vulnerabilities. The Jumo 004 engines required careful throttle management to avoid compressor stalls. Acceleration from idle to full power took approximately 8 seconds, eternity in air combat. Landing speeds exceeded 200 miles per hour, demanding long, straight approaches that made the aircraft vulnerable to Allied fighters during takeoff and landing phases. These limitations created a tactical paradox. The Me-262 was nearly invulnerable in level flight above 30,000 feet, but critically vulnerable during the approximately 10 minutes required for takeoff, climb to altitude, descent, and landing. Allied pilots quickly learned to patrol Me-262 airfields at dawn and dusk, catching the jets during these vulnerable phases, a tactic that accounted for approximately 70% of Me-262 combat losses despite the aircraft's speed advantage. The aircraft's actual combat record, when stripped of myth and examined through archival records, reveals a weapon of genuine tactical effectiveness but strategic irrelevance. Between August 1944 and May 1945, Me-262 pilots claimed approximately 542 Allied aircraft shot down, while losing about 100 Me-262s to all causes, a favorable exchange ratio that nonetheless represented a drop in the ocean compared to Allied production rates. During the same period, American factories produced over 15,000 P-51 Mustangs and 10,000 P-47 Thunderbolts, aircraft that could be replaced faster than they were lost. The Me-262's impact on bombing campaign effectiveness was negligible. Allied bomber losses actually increased slightly during the Me-262's operational period, not because of German success, but because bombing intensity increased as Allied forces advanced toward Germany. The weapon that might have altered air war dynamics in 1942 or 1943 arrived too late to matter in 1944, when Allied air superiority was already overwhelming and German fuel shortages restricted jet operations to a handful of sorties per day. The post-war fate of Me-262 technology reveals much about how military establishments process lessons from captured weapons. When American and British technical intelligence teams converged on German aircraft factories in April and May 1945, they approached the Me-262 not with awe but with professional curiosity tempered by recognition of its operational limitations. Operation Lusty, the USAF systematic effort to evaluate German aircraft, shipped 9 complete Me-262s to Wright Field in Ohio for exhaustive testing. American test pilots, including the legendary Chuck Yeager, confirmed the aircraft's speed advantage but also documented its handling quirks and engine limitations. The official evaluation report concluded, while the Me-262 represents a genuine engineering achievement in airframe design, its operational concept was flawed by late deployment, engine unreliability, and vulnerability during takeoff/landing phases. No direct adaptation of this aircraft is recommended for U.S. service, but its aerodynamic features warrant study for future jet designs. This sober assessment directly influenced American jet development, not through direct copying but through selective adaptation of proven features. The swept-wing configuration informed North American Aviation's F-86 Sabre design. The tricycle landing gear arrangement became standard for American jets. Even the cockpit layout influenced ergonomic standards for subsequent generations. Soviet evaluation followed a different path. The USSR captured Messerschmitt's Augsburg factory intact along with complete production tooling and several hundred Jumo 004 engines. Soviet engineers under Artem Mikoyan reverse-engineered the Me-262 into the MiG-9 jet fighter, a crude but functional adaptation that entered limited service in 1946. More significantly, German engineers captured by the Soviets, including Brunolf Bade, who had worked on Me-262 wing design, contributed directly to the MiG-15 development program. The MiG-15's distinctive swept-wing configuration and engine placement owed much to Me-262 aerodynamics, though Soviet engineers improved upon the German design with a more powerful Rolls-Royce Nene engine, acquired through British licensing before the Cold War intensified, and refined aerodynamics. The Me-262's most profound legacy thus emerged not in direct descendants but in the acceleration of global jet aviation development, a field that might have matured 5 to 10 years later without German wartime research. British jet development under Frank Whittle proceeded independently but benefited from captured German compressor designs that solved persistent efficiency problems. American jet programs gained confidence from Me-262 flight data that validated swept-wing theory at transonic speeds. Even the Me-262's failures proved instructive. Engine reliability problems highlighted the need for better high-temperature materials. Throttle response issues demonstrated the necessity of engine control systems that would eventually evolve into modern FADEC technology. vulnerability during takeoff and landing phases influenced airfield defense doctrines worldwide. Yet, this technological legacy carries an ethical dimension that cannot be ignored. The Me-262 was developed under a regime responsible for genocide, using resources extracted through forced labor and deployed in defense of a criminal state. To celebrate its engineering achievements without acknowledging this context risks normalizing the separation of technical brilliance from moral responsibility, a separation that enabled engineers throughout history to serve oppressive regimes while claiming political neutrality. Modern engineering ethics has developed frameworks for navigating these dilemmas. Concepts like dual-use technology assessment, responsible innovation, and value-sensitive design that require engineers to consider downstream consequences of their work, even when separated from end uses by organizational layers. The Me-262's history serves as a case study in what happens when these ethical frameworks are absent. Brilliant engineers solving fascinating technical problems while enabling a regime of unprecedented cruelty. This lesson remains urgently relevant as contemporary engineers develop artificial intelligence systems, autonomous weapons, and surveillance technologies that could serve both beneficial and oppressive purposes depending on governance structures. The scattered Me-262 airframes preserved in museums today, at the National Museum of the United States Air Force in Dayton, the Deutsches Museum in Munich, the RAF Museum in London, thus serve dual purposes. As artifacts of aviation history demonstrating genuine engineering achievement, and as moral reminders that technological progress without ethical constraint can serve destruction rather than human flourishing. Visitors seeing these aircraft should understand not merely their specifications but their context. That speed and innovation alone cannot overcome strategic errors or compensate for moral bankruptcy. That political interference in technical decisions can undermine even genuinely revolutionary technologies. That industrial capacity and production scalability often matter more than individual weapon performance in determining conflict outcomes. And most importantly, that engineers bear responsibility not merely for what they build but for the purposes their creations serve. The Me-262 that hangs in museum silence today was once the fastest operational aircraft in the world, a genuine milestone in human technological achievement. Yet it failed to alter history's course not because of engineering flaws, but because it served a lost cause, arrived too late, and existed within a system that valued spectacle over sustainability, quality over quantity, and political intuition over technical expertise. Its legacy is not one of triumph but of warning, a permanent reminder that technology divorced from wisdom becomes not salvation but spectacle, not liberation but liability, not progress but paradox. The jet that arrived too late thus teaches lessons more valuable than those from weapons that arrived on time. That timing matters as much as capability, that strategy trumps technology, that ethics must guide engineering, and that the most advanced weapon ever built cannot compensate for the fundamental errors of the system that created it. These lessons echo across decades into our own technological moment, a moment when artificial intelligence, biotechnology, and autonomous systems present capabilities whose consequences will depend not on their technical sophistication but on the wisdom with which humanity chooses to deploy them. The Me-262's silent fuselage in museum hangars thus speaks across time with urgent relevance. Build not merely what you can, but what you should. Innovate not merely for capability's sake, but for human flourishing's sake. And remember always that the most dangerous failure in engineering is not technical breakdown but moral abdication. The choice to solve fascinating problems while ignoring the purposes those solutions serve. This is the true legacy of the world's first operational jet fighter, not its speed records or combat claims, but its enduring warning about the inseparability of technical achievement from ethical responsibility in the human project of technological advancement. The engineering challenges confronting Messerschmitt's design team transcended conventional aircraft development and entered the realm of fundamental physics problem-solving under extreme resource constraints. A cascade of interlocking difficulties that required not merely technical skill but creative adaptation to material shortages, production limitations, and the relentless pressure of wartime urgency. When Willy Messerschmitt first committed company resources to jet fighter development in 1939, he faced skepticism not only from government officials but from within his own engineering staff, many of whom considered jet propulsion an impractical distraction from improving proven piston engine designs. The core aerodynamic problem was deceptively simple yet profoundly complex. How to design an airframe that could harness jet thrust efficiently while maintaining stability and control across a speed range where airflow behavior changed dramatically. Conventional wisdom held that propeller-driven aircraft faced insurmountable barriers near 450 miles per hour due to propeller tip speeds approaching supersonic velocities and compressibility effects causing control surface reversal. Jet propulsion theoretically bypassed the propeller limitation, but introduced new challenges in the transonic regime where airflow over wings and control surfaces created shockwaves that could render aircraft uncontrollable. Messerschmitt's chief aerodynamicist, Dr. Waldemar Voigt, approached this problem not through theoretical breakthrough but through exhaustive empirical testing, hundreds of wind tunnel runs at the Aerodynamische Versuchsanstalt in Göttingen using scale models with interchangeable wing sections, tail configurations, and engine nacelle placements. The breakthrough came not from a single insight but from incremental refinement. Testing revealed that moderate wing sweepback of approximately 18.5 degrees delayed the onset of compressibility effects by shifting the center of pressure rearward as speed increased, counteracting the natural pitch-up tendency that plagued straight-wing designs at high speeds. This solution was not adopted for transonic performance per se. The Me 262 never approached supersonic speeds in level flight, but for maintaining longitudinal stability through the critical 400 to 550 miles per hour range where combat maneuvering occurred. The wing's thickness-to-chord ratio of 12% represented another compromise between structural requirements and aerodynamic efficiency, thick enough to house fuel tanks and landing gear mechanisms, yet thin enough to minimize drag at high speeds. More significantly, the wing's structural design employed a single main spar positioned at approximately 30% chord, rather than the conventional two-spar arrangement, reducing weight while maintaining strength through careful calculation of load distribution. This innovation required developing new manufacturing techniques for forming the complex curved skin panels that transferred loads to the single spar, a process that initially caused production delays but ultimately proved successful. The fuselage design reflected Messerschmitt's philosophy of evolutionary rather than revolutionary engineering. Where possible, the team adapted proven solutions from earlier Messerschmitt fighters rather than inventing entirely new approaches. The semi-monocoque construction using aluminum alloy skin panels riveted to internal frames and stringers was identical in principle to the Bf-109, though scaled up significantly to accommodate the larger cockpit, fuel capacity, and internal volume required for jet engine ducting. The cockpit placement forward of the wing leading edge with excellent forward visibility, borrowed directly from the Bf-109's successful layout, though the Me 262's pressurized canopy represented a significant advancement in pilot comfort and high-altitude capability. Landing gear design posed particularly difficult challenges. The Me 262's high landing speed, approximately 110 knots compared to 80 knots for the Bf-109, demanded robust landing gear capable of absorbing significantly higher kinetic energy during touchdown. Conventional tail dragger configuration was rejected after wind tunnel testing revealed dangerous ground loop tendencies at high speeds. Tricycle gear was selected despite added complexity and weight because it provided directional stability during the critical landing roll phase. The nose gear retracted forward into a bay beneath the cockpit, a layout that required careful routing of control cables and hydraulic lines around the gear mechanism. Main gear retracted inward into wells in the wing center section, a configuration that maximized internal volume for fuel tanks while maintaining structural integrity through reinforced wing spars. The gear doors themselves presented unexpected difficulties. The aerodynamic loads at high speeds threatened to tear conventional hinge doors from their mounts, requiring development of a complex linkage system that synchronized door movement with gear extension and retraction. Engine integration represented the most persistent challenge throughout the Me 262's development. The decision to mount engines in the wing roots rather than in underwing nacelles, as on the British Gloucester Meteor, was driven by multiple factors. Reduced aerodynamic drag from eliminating external pylons, improved roll inertia for better maneuverability, and protection of engines from ground debris during takeoff and landing. Yet this configuration created severe maintenance difficulties. The entire wing center section had to be partially disassembled to access engine components for routine servicing, a process requiring 8 to 10 hours compared to 2 hours for nacelle-mounted engines. Engine air intake design required extensive wind tunnel testing to ensure smooth airflow into the compressors at high angles of attack, a condition that could cause compressor stalls and flameouts during aggressive maneuvering. The final intake configuration featured boundary layer splitter plates that diverted slow-moving air near the wing surface away from the intake lips, ensuring only high-energy airflow entered the engines. Exhaust nozzle design proved equally challenging. The high-velocity jet efflux created significant thrust asymmetry during single-engine operation, requiring careful shaping of the nozzle exits to minimize yawing moments. The Jumo 004 engine itself represented a masterpiece of engineering compromise under material constraints, a reality that fundamentally limited the Me-262's operational utility despite the airframe's excellence. Engine designer Anselm Franz faced severe shortages of nickel, chromium, and other alloying elements essential for high-temperature turbine blades due to their prioritization for U-boat diesel engines and tank armor production. His solution, fabricating turbine blades from mild steel coated with aluminum paint to reflect heat, was a desperate improvisation that limited blade life to approximately 25 operating hours before thermal fatigue cracks and life over the terrible beauty of destruction, perfectly engineered but perfectly unnecessary.